Hey, welcome to NASA Edge.
An inside and outside look at all things NASA.
Hey, we're here at NASA Langley Research Center in Hampton, Virginia, and right outside the Science Operations Center as we get set to, hopefully launch RaD-X today.
Well, I'm telling you, Chris, I understand your hesitation because we've been through this process numerous times, and because of weather and other things, we just haven't seen this balloon launch. But I tell you, it looks like all systems are go. The weather is good. The team is ready. We're underway. It looks like we'll see a launch today.
Hey, we were actually out in Fort Sumner back in, September 10th when it was supposed to launch. The RaD-X team was working hard out there. They were doing all their checks, getting ready. So it was a good time out there, but unfortunately, because of the winds, we couldn't get the RaD-X experiment launched, but we're ready to go.
And I'm glad you said winds because, it was beautiful out there. It was gorgeous weather. But those winds are really key in making sure that balloon can carry the payload where it needs to go all the way through the mission.
So in that case, a skeleton crew stayed out, is out at Fort Sumner, but we do have the majority of the team in the Science Operations Center, and that's where Franklin's located. And Franklin, how are things going?
Everything's great here in the Science Operations Center. Actually, on any other day, this would be the Flight Mission Support Center for any number of missions that are based here at NASA Langley Research Center. But today, the RaD-X team has renamed it the Science Operations Center, and hopefully, shortly, they will be receiving real-time data and science from RaD-X.
Very appropriate to name it the Science Operations Center because it looks like it's going to be data on demand for 24 hours after launch, which is a good thing.
I tell you what, it would have been really cool to actually be there in person to see this balloon launch because this is an 11 million cubic foot balloon. When stretched all the way up, it would be 1,000 feet when it launches, so it would have been cool to see that. But we know,
actually, when we were out there, you had the good fortune to speak with someone pretty key in this whole operation.
That's right. The Associate Administrator, John Grunsfeld, for the Science Mission Director, was out there. He got his start in balloons, and so he wanted to go out there and actually talk with the team members, see the experiment, see all the instruments on board. But I had a chance to sit down and talk with him, so let's check it out. So John, we're about to launch the RaD-X Science Experiment, and how is this experiment important to Science Mission Directorate?
The RaD-X experiment is different in a bunch of different ways, one of which, the primary, is that it's going to make a very interesting measurement of the radiation at the top of the atmosphere. We have aircraft underflying. We just had the ER-2 fly similar experiments, and then the chase aircraft with radiation detectors to try and learn more about the radiation transport through the atmosphere that as airline passengers or crew, we all experience when we travel in the atmosphere, high atmosphere, in aircraft flights. So that's the science objective. But it's also part of our hands-on project engineering. And so this is for engineers of all grades, people who are entering the workforce, people who are experienced, to work on a real flight experiment. And it's kind of like an Indy race car. They've been working for 3 years now. They have to propose, they have to get accepted, they have to use all of our great systems engineering processes to get to race day. And the balloon lifting off is the start of the race. And so it's that excitement, that romance of real science, real engineering.
Now, I understand that you were in that same position many, many years ago, and you started off with balloons.
That's exactly right. I started off life as an undergraduate in college thinking I was going to be a theoretical physicist. And one of my advisors gave me very sage advice. He said, sometime during your life, if you want to be a great theorist, you have to understand experiments, because of course that's what theories are balanced against. And he said you should do a thesis, undergraduate thesis in experimental physics, so you learn about the process of measurement, kind of like RaD-X. And I did an experiment. It was a high-altitude balloon experiment, an X-ray astronomy experiment, and it absolutely transformed my life because I found that it was much more interesting than any of the other physics I was doing. It was just personally exciting and kind of the romance of science I discovered through scientific ballooning. And I went on to do graduate school and my postdoctoral work using high-altitude balloons to do my research. When I became an astronaut, I found that most of the skills that I learned doing high-altitude ballooning, building the telemetry systems, the communication systems, working on computers, working on pointing systems, working on the instruments, translated directly to my space shuttle experience. And even on the Hubble servicing missions, working in a spacesuit, trying to reach connectors that were hard to get at, reminded me of working on balloon payloads on the flight line, race day, reaching in and getting the payload ready to go, and then sending it off to do its mission.
So John, you had a chance to fly in an airplane and get a tour of Fort Sumner.
Yep, so I had a chance to fly in the NASA chase plane. This is the aircraft that has command and telemetry. When we get ready to terminate the balloon at the end of the flight, bring it down and then have the payload, RaD-X, come down under a parachute, it has the ability to send those terminate commands. The balloon is going to go wherever the wind takes it. And if it takes it further than the radio antenna on the top of the tower can communicate with it, then we have the aircraft to do that. So we went out, checked the communications, and also checked out the general airport area around Fort Sumner. And you really get a good appreciation for why Fort Sumner is a great place to fly balloons, because it's ranch land and open land, you know, for as far as the eye can see.
But also, you had a very special instrument on board that's actually flying on the RaD-X mission.
That's right. So in the back of the aircraft is the tissue equivalent proportional counter, and that's flying on the RaD-X instrument. And I've also been able to fly that on my space shuttle missions. In fact, I was the guy that turned it on and checked it all out at the beginning of the flight, and at the end of the flight turned it off. And that's part of the broader science from RaD-X, which is to compare the radiation at the top of the atmosphere, which the balloon will do, to the radiation that the aircraft flying much lower in the atmosphere will experience, to do that calibration down through the atmosphere. Because after all, RaD-X is helping us to learn about how radiation is transported to the atmosphere, where pilots, flight crews, and passengers like us will fly on commercial aircraft.
So you can't get away from that instrument because you were actually helping out the RaD-X team in the air today by turning on the instrument.
That's right.
Well, John, thank you so much for joining us today. We really appreciate your time. I know
My
you're a busy
pleasure.
person, and we'll see you out for the launch.
Go RaD-X.
We're here with Ryan Norman, who's a member of the science team for RaD-X. Now, I understand that what we're looking at in RaD-X is sort of radiation at very high up in the atmosphere.
Correct.
And then looking at it as it changes, as it moves through. So how is RaD-X going to help us do that?
So RaD-X is going to fly at 2 different altitudes. So we're going to start off at really high altitudes, and then we're going to valve down about 12 hours later to get a different altitude. And the point is that the radiation, as it interacts in the atmosphere, changes with altitude. And so the balloon is going to measure at 2 different altitudes to try to give us 2 different data points on the radiation levels, and so that we can help build our models better.
Okay, so I understand that there are other assets gathering data sort of at the same time. Does that mean that you have to fly those assets sort of in the same general vicinity as RaD-X?
We want to be in the same area and fairly close in time. The space radiation environment doesn't change much in time. Day to day, it's pretty much the same. So as long as we fly in reasonable temporal vicinity, we'll be good. And we want to be in the reasonable geographic area also. So we want to fly close to where the balloon will be flying.
Once you fly RaD-X and you get the data from very high to the valve down area to the other assets, what are you going to do with that data? How do you use that to our benefit?
So we want to use this data to develop better models to help characterize the radiation environment in the atmosphere. We want to quantify the radiation received by airline crews, and we have a whole model called NERIS that's set up to do that in sort of real time. And it's built on this notion of terrestrial weather, where we're going to take data in real time from the space environment outside the Earth's atmosphere to hopefully data on airplanes in real time, ingest all that data and figure out what, say we're flying back to Albuquerque to launch RaD-X2.
Yeah, right.
And,
good plan,
And we want to know what our radiation dose is on that flight. NERIS gives us that information. So it tells us the dose that the air crew or the people on the plane might receive at any given moment.
Awesome. Well, I know you're going to get great data. Very excited about it. Thanks so much, and we look forward to good results from RaD-X.
We're very excited, and hopefully we get off the ground today.
Awesome. Well, we had a chance before we even went out to Fort Sumner to talk to some of the other team members from RaD-X. Let's check it out.
So Kevin, what's your role in RaD-X?
So my role on RaD-X is the project manager. As the project manager, I get to work on a day-to-day basis to keep an eye on our funding, keep an eye on our resources and our personnel, to make sure that everybody on the team has exactly what they need when they need it.
So what you're telling me is you're the top dog.
I am the top dog. I'm the head cheese. So on a day-to-day basis, it's great because as a training opportunity, I've gotten the ability to step up into this role when normally I wouldn't get such an opportunity. But to run the meetings, to lead the team, and get to have them report on up. But then also I do get to turn around and talk to our program office and talk to our other stakeholders to make sure that I keep them in the loop at the same time.
At this point, what's been the most rewarding part?
I've actually gotten to see a lot of growth out of some of the younger individuals who came on board. At the very beginning, with a new team put together, you just never know how things are really going to play out. But looking at the individuals as they've gotten to come along, it's kind of been nice to take some of my experiences, my past experiences, and pass those on to even some of them. Even though I am myself a very early career individual, So to be able to do that and then see the payload come together, the most rewarding part of the payload coming together is seeing the hardware start to work, seeing us get out there, and then that leads into doing things like the mission simulations that we're working on this week.
What does that entail? And it seems from covering it, it's an all-day event.
So for a mission simulation, what we do is we get started at 7 in the morning where the team meets around the payload. We then talk about what we're going to do for the day. For example, during one of the recent mission simulations, we took the payload outside, out to the pavilion where we could get a satellite connection. We use the satellites to communicate, to bring the data down in real time so that we can monitor the health and status of the payload and also get some of our science data back in real time. Once the payload is outside, we get set up for the day. We talk a little bit more about what we're going to do. We make sure that everything is set up and running. Then some of us move over to what we call the Mission Operations Center or the Science Operations Center. That is where the data comes down to. So when the data is collected on the payload, it's transmitted up to satellites and it comes back down to Earth. At that point, it is received into our Mission Operations Center. Okay. The individuals in the Mission Operations Center during a simulation are trying to watch and practice what they're actually going to see during the actual flight. So the team gets to spend some time watching the payload, they get to spend time sending commands to the payload and practicing the day-to-day routines that we'll use when we actually fly.
So James, what's your role in the RaD-X project?
So I'm the avionics lead, which means that I'm in charge of all the electronics on the project. Avionics is just a fancy term for saying aviation electronics. So any electronics that fly in a flight environment. And so in that role, I am in charge of making sure that all the science instruments interface appropriately with the electronics, that we're collecting all the data that we need, and that we're getting all the health and status information that we need on the ground.
So it sounds like a pretty big role because I'm sure there's a lot of electronics involved in the experiment.
Yeah. We have 4 different science instruments that are collecting data, but then to make sure that they're operating nominally, we have a lot of support electronics, such as a thermal control system and various other measurements that we're making so that we can be sure on the ground that the system's actually operating nominally.
Now, will you also be responsible for getting that data from the system once you recover it and then giving it to the science leads?
Yeah, certainly. The way that we have the mission set up, our onboard system is actually our main way for recovering the data. So when we recover the payload, depending on what state it's in, there's a few different paths we could take, but I'll be involved in making sure that we get the data off and get it to the science team.
So one final question, kind of just reflect on this whole process, getting involved initially with RaD-X and up to this point now where you're ready for flight. How's that experience been for you?
Oh, it's been a great experience, especially coming into NASA fresh out. So far, my NASA experience has very much been defined by this project, and we've had a great team, really great leadership, and I've had a really good chance to get hands-on experience working with other disciplines and really taking responsibility. So I've grown a lot as an engineer and as a NASA employee as well.
So Denisse, we have a big launch coming up. So what's your role in RaD-X?
Sure, so my role is the integration and test engineer. So part of my task is to ensure that all the components that have been individually designed come together. Then we test them in similar environments that like we're going to do in flight, and that gives us confidence going into the launch that all of our electronics and all our data is going to function as we should.
Now, you're a part of this HOPE program.
Yes.
Kind of tell us a little bit how you got involved with HOPE and your experiences so far.
HOPE has been probably one of the most amazing things in my personal experience that the agency has done. Typically for a lot of the bigger projects, they take 5-10 years maybe from concept to launch. RaD-X really was able to go from concept to launch in a very short period of time. Right. And what that does for us as engineers, young engineers, is give us visibility to the other disciplines. In the previous years working on other projects, I didn't have much exposure to thermal engineering, electrical engineering, avionics design, structural design. And so being able to see that progression really gave me an appreciation of the way that NASA works and how flight projects operate.
And joining us now is the Chief Engineer, Amanda Cutright. Amanda, how you doing?
I'm doing great. Today's a great day to launch a balloon.
Absolutely. It's been a long time since September 10th was the first date. We had a chance to launch it, and now we're here.
That's right.
But it's going to go, isn't it?
It is. It's going to go today. I can feel it. It feels like a launch day. It looks like a launch day. So
now, tell me, as Chief Engineer, what is your role in RaD-X?
So my role is as the technical lead for the project. So once the science team has defined where we need to go explore and why, and what data we need to collect, I get to work with the engineering team to design the system, to analyze it, build it, integrate it, test it, and get it integrated out at the launch site to make sure that it's going to survive in the environment that it's going to go to. So.
Now, just to kind of recap, we're in about a 15-minute delay for launch. So they usually inflate about a half an hour before launch?
That's absolutely right. Yes, right now they've just been doing the preparations, getting the equipment. The payload is out on the flight line right now. I think you've probably had a picture of that right there. Yep, so that's the helium tanks that are out there. So our payload is on right now. We've actually been streaming health and monitoring data for the past couple hours. So everything looks good. We're on. While our satellite is on, we're going through an Iridium satellite service to collect the data, and everything right now is working nominally. We're really pleased.
Now, to kind of take us through the plan, once that balloon launches, kind of tell us exactly where it's going to go, where it's going to end up.
Sure. So as you're seeing in the animation, we're actually on before Big Bill launches us. So the Big Bill will let us go, and we will remain on as the balloon ascends. We will go up to an altitude that our science team has defined as having the balloon go above 105,000 feet. It will stay up there during the day, and we will watch the sun set. You can see in the time lapse here. At nighttime, we will also be doing a little bit of a valving down, so we'll let some helium out of the balloon to get to that second altitude. And then after we've collected data for enough time and observed the sun rise, the balloon will cut away and the parachute will let us descend safely onto the ground, and we will go recover the components of the payload.
And I believe, and correct me if I'm wrong, but one of the reasons for that 15-minute delay is because as you launch the balloon, it's going to be heading east initially.
That's right.
And you don't want to devalve, I guess, overpopulated area?
That's right. That's correct. So each day they do a weather prediction for us so that it's up to date. And what they decided this morning was to just delay us a little bit so that valve down can occur. When we valve down, we'll actually start floating more westerly, which will enable us to get all of our science data that we want at that second region.
Now, do we have a prediction where we think it's going to land?
It depends.
That's the big question, right?
That is the big question. Right now, we're estimating that it actually might not be terribly far away from where we're taking off in Fort Sumner, maybe just a couple-hour drive here or there.
In some cases, you could drive 6, 7, 8 hours to get your balloon, right?
That's right, yes. Sometimes when they predict the balloon is going to go further downrange, the recovery team will leave as soon as the balloon launches.
That's right.
So in this case, we have some of our team members will help out at the Mission Operations Center monitoring the payload because we believe it's going to come back over. It'll go a little bit north, maybe a little bit west, east first, little north, little west, and then we'll look forward to recovering it and getting our data.
Well, Amanda, thank you so much for joining us. I know you have a lot of work to do in the SOC, and we'll get you back to your work. But coming up next, Blair had a chance to sit down with 3 more RaD-X team members, so let's check it out.
We're here at NASA Langley Research Center with Becky Stavely, who works with RaD-X. Becky, I understand you're a thermal engineer. What do you do as a thermal engineer?
Well, the role of the thermal engineer is to make sure things don't get too hot or too cold. So we do a lot of analysis looking at, for example, how your computer gets too hot, you can hear the fan turn on. We do analysis to make sure that those fan systems and any other system is working to make sure that nothing gets outside of its operating range, because it can break if that happens.
Now, is that for all the instruments and things on board for RaD-X?
Yeah, all of the electronics have different operating temperatures. Some of them are narrower than others, specifically the science detectors. Some of them are very sensitive to different temperature ranges. So we put it into a specialized chamber that we can control the environment temperature and just try to get as close as we can to what we think the payload will experience in flight and just show that it will operate as close to the environment as possible.
And I'm assuming, based on the fact that everybody I've seen with RaD-X is happy right now, that the tests have gone well in terms of being able to meet those requirements.
Yes, it's made everyone very happy. So it gives us a lot of confidence that when it gets up there, it will work.
Hobart, I know there are lots of software being deployed in a mission like this, but communication is a big deal, especially on a mission like this where you have a spacecraft in flight sharing data. Tell me a little bit about the process for RaD-X. What's happening during the test in terms of managing that data and delivering it?
So during the test, we're taking our payload outside so that we could get a good signal to the Iridium satellites that are orbiting overhead. And the data packets would be produced by the flight software, and it would be produced by interacting with the instruments on board, getting data from the instruments and packetizing that data into basically a little file that it can just ship over the network.
I love that term, packetize.
Yep.
I want to get to a point in my career where I'm packetizing things, but please continue.
So we take the packets and we send them through the modem, and they go to the satellite network. And we kind of view Iridium as a black box. We don't really know what goes on in it. As long as it works, we're happy with it. But it goes from their satellites, possibly through multiple of their satellites, down to their ground station. And then we can just use the regular internet to connect to their ground station through the TCP/IP protocol. And then our ground software can contact their ground station and receive those data packets. And then once we have those data packets, we save them to our computer, we display them on the graphical user interface so that we can see like all the temperature data, so that we can check to make sure the instruments are okay, none of them are burning up.
This is already vastly more sophisticated than any computer abilities that I have. So how difficult is it to manage all of those aspects of the data through the software for a mission like this?
It was a lot more difficult than I thought it would be, which I guess is par for the course, because this was a very good learning experience, sort of learning the various processes.
Erica, Hobart mentioned that there are a lot of significant challenges for the software team on this project. What are some of the challenges that you face from the science side?
I would say some of the challenges that we're going to experience are things we really can't account for. We could experience drift. There's a certain area longitudinally and latitudinally that we need to stay within, and if we drift outside those areas, it can make it a little bit more difficult for us to analyze the data and help correlate it back with the nearest model. Another challenge we could potentially face is, one of the instruments could do something really weird that we didn't anticipate. And so those are things that we would have to make sure we pay attention to, log them so that when it comes time for the analysis, we can really discern whether this is spurious data or good data, and we can kind of make that judgment call. So I would say the stuff we can't control, which is the physical location of the payload at any given time, as well as some of the downstream data issues that we might have anticipated would be the biggest challenges for the science.
On the day of the launch, you're going to be at the Flight Mission Support Center. What is your role on test day?
So on test day, I get to fulfill my other role, which is the Education and Public Outreach Lead. That'll be part of my job and responsibility to head that up. The other part will be, as I said, the missions lead, the shift lead during that shift. So it'll be monitoring the status of the instruments, looking at the science data that's coming down, and communicating back in New Mexico with the Mission Operations Center to let them know if we're seeing any weird anomalies with the data.
Now, how do you feel in that role, allowing Franklin to be in the FMSC with a camera during the mission? Is that going to be acceptable, or are we going to be able to do that legitimately?
I will try to be on my best behavior.
Okay.
I will absolutely try to be on my best behavior.
Okay, well, if you have to discipline him in any way, make sure it's when the cameras are running.
I was actually going to say, I got to watch my potty mouth.
Okay, yeah, definitely got to watch that.
Yeah.
It's a family show. It's a family show.
And if it's live broadcast, I really have to be on my P's and Q's.
Well,
I'm going to get some coffee that morning.
We will be there to hope that you're on your P's and Q's, but if you're not, we can't stop it. So, it'll be interesting. The mission will be a success, but who knows about the broadcast.
Yeah. That'll make for some interesting TV.
Hey, as we get set to launch RaD-X, Franklin is in the Science Operations Center. And Franklin, what's going on?
The mood is great in here in the Science Operations Center. It's actually standing room only. It's filling up. Everybody's getting ready for the filling of the balloons so that they can get RaD-X off the ground.
And talking about balloons, you know a little bit about balloons.
Yes, actually, over the summer, I rode up to the Wallace Flight Facility and talked to the chief of the Balloon Project Office about the balloons and how they'll actually get RaD-X off the ground. I'm here with Debbie Fairbrother, who is the chief of the NASA Balloon Program Office. How you doing, Debbie?
Hi, I'm great.
I was over at your lab earlier today, and I noticed that you had a couple of different balloons on display. You have the zero pressure and the super pressure balloon. Which one are you going to use for this experiment?
For this mission, we'll be flying on a zero pressure balloon.
What's the difference between the two?
The zero pressure balloon is a vented system, so it's basically zero differential pressure at the base of the balloon. A super pressure balloon is a pressurized system, much like your car tire. And the difference is, with a zero pressure balloon, if the sun goes down, the gases in the balloon cool, you're going to contract and you're going to lose altitude. In a super pressure balloon, as long as you're pressurized during the day, when the sun goes down, you're going to lose pressure. But as long as I maintain a positive differential pressure across the envelope, you'll float at the same constant density altitude.
Well, in this experiment, the balloon will have to go up and then come down during the course of the 24-hour period. Tell me a little bit about how that will be done.
Exactly. RaD-X is a little unique for us because they have basically two altitudes of target. They want to float at a high altitude during the day, and then at night they want to come down to a secondary altitude and stay stable at that altitude during the night. So it's a little bit different. We've had to do a lot of simulations. We're flying a balloon that has 3 valves on the top so that we can let off more gas quickly if we need to.
It's not like a hot air balloon, is it?
No, no. So our balloons are helium.
Okay, all right.
So we're not bringing any heat source to it, but they are heated by the sun.
Okay.
And the helium is our lift gas. How we fill it is we have inflation tubes, and in a zero pressure balloon, they go into the side wall of the balloon, so kind of through the shoulder of the balloon.
So it looks like the balloon has sleeves.
Yeah, I mean, so it's they're kind of dangling, and then at the end, one of the keys that you see in an inflation is the tubes are still attached and kind of rigid, you know you're still inflating.
Right.
If they've been, stopped inflation and tied it off and cut it away and they're just kind of hanging, you know you're close to launch.
So I'm assuming you have GPS on the payload and that's how you track it?
Right, so through the NASA Balloon Program and the Columbia Scientific Balloon Facility, we provide the command and control. So we have all of the electronics on board to know where the balloon is, as well as how to terminate it. So we've got all of the command and control of the mission.
So you mean terminate if it were to start moving toward like Mexico?
Right, and even at the end of the flight. So if it's going in a direction we don't want to, or when the science is over and we need to bring it down, we have that capability.
Venting.
Well, actually, no. To terminate, what we do is it's fun. We actually send a command to separate the bottom of the balloon from the top of the parachute, which in turn rips a panel open in the balloon. So the payload will come down to the ground on the parachute, and the balloon will free fall. And we'll go and recover both items.
Is the balloon you're flying a weather balloon?
No. We're flying a scientific research balloon. Typically, a weather balloon will go up and pop. Oftentimes they're made out of a latex material, so it'll go up, expand, 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 and pop. Our balloons go up and float, and so typically the science is done once you reach the stable float altitude. So we often say a weather balloon goes up and pops, and the NASA balloons go up and stay a while.
So Franklin, with your experience with balloons down and interviewing Deb Fairbrother, give us your thoughts. I mean, this balloon looks. It's kind of hard to judge the size of the balloon on the screen, but it looks like it's a pretty big balloon from here.
Yes, actually, it really is. You guys had an opportunity. Hey, there it is.
Yeah, there you go. Wow, that's pretty impressive, isn't it?
Okay, see, that's what they mean by big. See, now you got to get back and see the whole thing. Oh, yeah, wow. Oh, that is awesome.
So now Big Bill is driving to make sure that it's in the right alignment before it releases.
Look at him go. There he goes. Awesome job.
And the folks from Fort Sumner from the Columbia Scientific Balloon Facility is offering this program feed right now for us. He's
there we go.
Operating the camera. And there goes the balloon.
Look at that. See, now that gives you a better sense of the scale.
That's right.
How huge that is. Oh, lots of emotion in the room in there. Oh, look, check it out. Sorry. Little enthusiasm there. There's the onboard camera. That's awesome.
This ends our broadcast for the Radiation Dosimetry Experiment, or RaD-X. I'm glad you had a chance to join us.
And we look forward to hearing from you guys. If you have questions, comments through Facebook and Twitter, either way, let us know. We'll try to get answers out to you guys. Not from us, don't worry. It'll be from...
You're not going to answer the questions right now.
I won't answer myself.
Well, that's good to know.
For your benefit.
Okay.
But just thanks for joining in. Thanks for experiencing this great moment for RaD-X along with us today.
You're watching NASA Edge.
An inside and outside look at all things NASA. Wow, stereo.
Yes.